Just do my theatricals.
I'm now in the middle.
Smack.
And I'm like,
Yeah, it's just like an arrow, like a spear. All right, maybe we could just get started. All right, everybody, good afternoon. It is my great pleasure to introduce today's speaker, Jonathan Lin. Jonathan got his PhD from MIT, working with Carrie Emanuel. He did some pretty interesting work, if I say so myself, on Troposphere-Stratosphere interactions on the Madden-Julian Oscillation, for what he will be talking to us today. Right now, Jonathan is a postdoc working at the Lamont-Doherty Earth Observatory and Columbia University. Jonathan you just recently accepted a position, faculty position at Cornell University, so congratulations on that. So without any further ado, I will keep the introduction short. Take it away.
Thanks for having me, everyone. It's always exciting when people want to know about what you're doing. Yeah, I'm very happy to be talking to you guys today about troposphere-stratosphere interactions. And hopefully after today, I'll convince you that there is some form of importance of the stratosphere, especially playing a role in modulating the troposphere. Even though this is a well-known phenomenon that happens in the extratropics, it's less known in the tropical atmosphere. And you know, I hope this is not super formal, so feel free to ask me questions if things are unclear. And of course, you know, a lot of this work was done somewhat with Carrie and somewhat with over my, you know, brief hiatus between PhD and my postdoc. So, you know, of course, this work wouldn't be possible with all the mentorship and advice I had over that time. And so, because I'm at UW, I figured out that UW is the University of Washington, UW is Wisconsin. But we play this. So this is just satellite, but I mean, this is, there are people probably here, people know here that know more about these images than I do. But my impression is that they're just stitched satellite images, and you can see, you know, I just like to start all my talks off with, you know, with observations, and there's a ton of variability in the atmosphere. You know, the tropics, you have some beautiful satellite imagery of extratropical cyclones. And in the tropics, there's, you know, things look kind of chaotic. You know, this is in March, so you'll see some tropical cyclones here, but there's a lot of, you know, it looks like there's a lot of chaotic variability. We can take a little step further beyond observations and look at reanalysis data. So here, reanalysis data, obviously, it's not observations, it's simulated observations. But something we can consider as kind of the ground truth. And here, what I'm showing is outgoing long-wave radiation. So the amount of energy that Earth is radiating to space. So basically, the darker the color, it's a kind of a proxy for more convection or precipitation. And this is over the course of September 2017. So here you can see this is one of the infamous Atlantic hurricane seasons. So there's a lot of hurricanes here. But if you focus in on the tropics, you know, you can see a lot of variability. You know, things are moving westward. There's some things moving eastward. There's a lot of, you know, convection over the maritime continent region, and it just kind of looks like chaos. And we've known this for a long time now, but there's a lot of actual order in this chaos. And you know, I'm showing you a month-long time scale, and that's typically what we consider intra-seasonal variability. So variations less than a month or less than a season. And we've known for a while now that there's actually a rich spectrum of intra-seasonal variability in the tropical atmosphere. And so, you know, if you're familiar with wave number frequency diagrams, but basically you could take this information here and filter it for waves of a certain scale and waves that propagate at a certain frequency. And what you don't see here is that there's a huge red noise spectrum, but you can filter out the background, and basically what you get are these peaks in the wave number frequency spectrum. And there's the Kelvin waves, there's equatorial Rossby waves, which you define, inertial gravity waves. This is only the symmetric spectrum. And these equatorial waves have been predicted by simple linear theory long before we had observations of them. So this dates all the way back to Matsuno's work in 1966, except for the MJO, which I'll talk a little about later. But what I first wanted to talk about is that these models that predict these equatorial waves. So what I want to point out is that all these solid lines here are actually predictions from the simple, really simple shallow water models of the tropics. And it's very amazing that they line up really well. I think this is just really remarkable finding. But these models are rigid width models. Basically, they just assume that there's zero upward motion at the top of the troposphere. And that's really simple because you don't want to deal with anything above that. You just assume that there's no interaction with the layer above, and it makes things really simple. The boundary conditions are really easy. But that's not actually what happens. In the real world, of course, as we know, there's a stratosphere and a troposphere. The troposphere, as we know, it's warm, it's moist, there's interaction with the surface, there's interactions with mountain, the ocean. It's where we live, so we really care about the troposphere. It's where all the weather occurs, or most of the weather occurs. But of course, there's a stratosphere, which is much colder, drier, and it's much more passive. There's not a lot of dynamic weather that happens in the stratosphere. But there's a lot of important things that happen. For instance, the ozone layers in the stratosphere. Many people know about the ozone layer. And when things go on in the troposphere, they like to interact. They don't just stop at the tropopause, which is the boundary between the two. Things like to interact, and there's energy that radiates upwards. There's all kinds of interactions. And when you make a rigid lid approximation, you're literally putting a lid on this, and there's no interaction. And so the questions I hope to answer today is what about interactions with the stratosphere? Are they important in the tropics, and do we need to care about them? And I'll be approaching this mostly from a theoretical perspective, although I have some cool simulations later, but most of this stuff is theoretical work, and I'll try not to bore you with too many equations, but there will be some just because of the nature of what I do. So the first part of the talk we'll be building the simple theoretical model from scratch and talking about looking at how the stratosphere affects equatorial waves, or intra-seasonal variability. And in the second part, I'll talk about this really big problem right now in the field, which is how the stratosphere actually is observed to modulate the strength of the Madden-Julian Oscillation, which I think the answer has been eluding us for a while. And then I'll have some comments at the end. And so the first part of this work has been published earlier this year. So what I want to start with in the tropics, a really important core principle of the tropics is convective quasi-equilibrium. And basically, to convince you of this, here's a plot of, on the right, it's the solid line is the lower tropospheric density temperature, and the dashed line is the upper tropospheric density temperature plus 34 Kelvin, just for the offset. And this is over the course of around a year. So the lower tropospheric is between 900 and 500 hectopascal, and the upper troposphere is above that. But basically what you want to see is that there's a huge variation in the density temperature, or covariation between the two lines in density temperature. And what this is saying is that energy is being redistributed in the vertical constantly. It's being constantly redistributed in the vertical. And that's the idea of convective quasi-equilibrium. It's a statistical hypothesis. So it's a statistical equilibrium. I really like the boiling pot analogy. So you have a boiling pot of water. It's being heated from the bottom, and things become unstable because you have cooling from the top of the surface, just like in the real atmosphere we have radiative cooling, we lose energy to space. And because of this cooling, things naturally get recycled so that you can think of, in a statistical equilibrium sense, the temperature of the water is the same. Now the temperature, so here in the water, the temperature is the conserved quantity, but in the real atmosphere, it's a different variable, but it's kind of the same idea where you have this constant overturning of the circulation. And this quasi-equilibrium has really strong implications in that it means that the vertical temperature profile is approximately moist adiabatic. And when I was talking about conserved quantities now, you don't have to know what the saturation moist entropy is, or people might think of the moist static energy, just a different quantity. But it means that a certain quantity, in this case it's a saturation moist entropy, is constant with height. The boiling pot analogy is the temperature that's constant with height. So when you apply strict quasi-equilibrium to hydrostatic motion, you get this equation here for the geopotential. And it's a function of two terms here. The first term is, in the brackets, is a vertical average. So it's the vertical average of your column. You think of it as the mean state of your column. And we'll just call this the barotropic mode. You'll just have to stick with it for now. And the other term is the temperature minus the mean temperature. So it's the deviation of the temperature from the mean profile. And we'll call this the barotonic mode. And when you make this really simple, this is an actually very, very simple theoretical equation. It's just telling me that there's two modes in the tropics, and these modes are what help determine the vertical structure in the tropical atmosphere. And so to help build some intuition for these modes, this is not always easy, I find, but the Barotropic mode, so we'll talk about the Barotropic mode first. So what I'm plotting here is just a vertical cross-section. Imagine you have a wave number, just a wave in x, and this is a wave in x with the Barotropic mode in the vertical, where the colors are the zonal wind and the contours of the vertical velocity. And so here you imagine you have easterlies here, westerlies, so there's going to be convergence in the boundary layer. Associated with that convergence is the vertical velocity. The vertical velocity peaks in the middle of the troposphere and it decays as you go up, and it's 0 at the top. And that's the Barotropic mode. There's no vertical motion at the tropopause, and this is, if you're familiar with the tropics, it's just a deep convective mode. Now the other mode is the barotropic mode, and this you can see here, the wind is constant with height because it's just the mean, it's the mean of your column. And you have, again, you have convergence at the same location, but now instead of if you assume that the vertical velocity is 0 at the surface, right, you can't have vertical velocity into the surface. As you move upwards, actually, the vertical velocity increases, and it's non-zero at the tropopause. And I'll call this the Troposphere-Stratosphere mode, because now you have non-zero vertical velocity at the tropopause, which allows there to be interaction. And you can imagine if you put a lid at the top, right, you won't have a barotropic mode. It just will not be excited. And so you can only get a barotropic mode. And this is why I think shallow water models work really well in the tropics, because to a good approximation, things are, rigid lid is a good approximation, and you have a single vertical mode, so you can boil down everything to just the shallow water equation. But there are actually interactions with the stratosphere, and what I want to ask is, how do troposphere-stratosphere interactions affect tropical interseasonal variability? And the goal here is to couple a quasi-equilibrium troposphere model to a equation set for the stratosphere. And so you can imagine what we're trying to do is that there's a troposphere where it's convecting, there's precipitation. You have a tropopause that's actually interactive, and you have a stratosphere above that where there's going to be interactions between the troposphere and the stratosphere. And so the first thing we're going to do is write the equations for the troposphere. You can do, decomposition of the vertical modes, so we know that there's only two vertical modes, right? The barotropic mode is simple. It's just a constant with height. And the barotropic mode right here is the temperature minus the average temperature. And you just assume that every single variable is just this linear superposition of the barotropic mode and the first barotropic mode. So if you're familiar with two-layer models, for instance, this is exactly what a two-layer model does. So I'll show these equations here. I mean, I'm not going to explain them in depth. If you're familiar with them, that's awesome. It's not necessary to understand them at its core to understand what's going on. You have the linearized non-dimensional momentum equations. So the first two are just for the barotropic mode, and the second two are for the barotropic mode. Note here that this is the barotropic geopotential, and this is the saturation entropy. That's the pressure variable in the barotropic mode, and that's because of quasi-equilibrium. And of course, you have your mass continuity equation here in pressure coordinates. It's coupled to the thermodynamic equations, and this is not as important for the stuff we're doing in this section, but basically, you have an equation for the saturation entropy. It's a boundary layer quasi-equilibrium for those that care about those details. And then an equation for the column integrated moist entropy, which is a function of your boundary inputs like radiation, vertical convection, and surface temperature flux. But this is not, if you don't understand this, it's totally fine. There's a lot of jargon. Okay, so the stratosphere, we're going to just use the linearized non-dimensional log pressure stratosphere coordinates. So the stratosphere is dry and passive, and it's in hydrostatic balance. So the equations actually look quite familiar. The thing I want to point out here, so this is the momentum equations, the continuity equation. You have a temperature equation, and you assume that the density falls off with some scale height. This is all non-dimensional, so things up. Yes?
Where's the delta X come from?
Oh, delta X is a zonal geostrophy term. It's just like the Mariana length scale. It's a ratio, aspect ratio, basically. So if it's, for the real Earth, it's around 30. But you can take, if you take this to infinity, then it's basically zonal geostrophy, so this term is 0. But I left it in there for details, but it's not super important. But just an aspect ratio. It's a function of like the Earth radius, the Coriolis force. And sorry, not Coriolis force, beta, the beta. Okay, and the thing that I want to highlight here, S here, is the non-dimensional stratification. So it's a measure of how stratified the stratosphere is. You can think of it as a buoyancy frequency. It's a non-dimensional buoyancy frequency. Okay, so that's, I know that was a lot to digest all at once, but, and it's not super important to get all the details correct. Just know on a high level, we're coupling a convecting troposphere with a dry and passive stratosphere. And classical, so you have to couple the two together. So basically, the coupling conditions are saying that the geopotential is continuous across the interface, and the vertical velocity is continuous across the interface. Yeah.
John, what assumptions about the stratosphere that you make are you uncomfortable with?
What assumptions am I making?
Yeah, because it is a little bit above what I'm thinking. I just want to know what you think. What things in there are suspect in your mind? Or maybe the answer is nothing. I don't know.
Not much. I mean, these equations are actually really good in
Okay.
the stratosphere. The log pressure coordinates, that's where the stratification is more or less constant with height. But there are other things that go on in the stratosphere, for instance, radiated damping, that might affect some of the results.
Okay.
But actually, the thing I'm most uncomfortable with is the fact that you assume that there's an infinitesimal jump between tropospheric dynamics and stratospheric dynamics.
Okay.
In the real world, there is a transition layer. It's not easy to model a transition layer, but that's the thing that's the biggest problem.
Okay. Thanks.
Yeah.
I'm sorry, but what's the passive stratosphere again? Like, I cannot follow what you mean by passive stratosphere.
Passive as in, it just reacts to a bottom-up forcing. So weather systems don't just appear in the stratosphere like they do in the troposphere. They typically, weather systems radiate upwards from the troposphere into the stratosphere. That's what I mean by passive. Does that make sense?
Yeah.
Okay, cool. So we have a way to couple them. There's a lot of underlying math that I'm glossing over because it's boring, but that's what we do. So basically, we've coupled a convecting troposphere to a dry passive stratosphere. It's all linear dynamics. You can imagine this is the model that we're doing, schematic. Oh, whoops. It's very complicated. There's 8 total prognostic variables. It's a really complex system. But with certain approximations, you can have analytic solutions, like if you assume that the meridional wind is 0, for instance. And we're going to use a computer to solve the rest because the computer is smarter than I am. And this is what a solution looks like. This is one kind of wave. It's called a Kelvin wave in the tropics. And this is the solution when you assume that the meridional wind is 0. And so here, what I'm showing, the solid lines are the geopotential, the arrows are the zonal wind, and the colors are the pressure vertical velocity. Later in the talk, I'll use the actual vertical velocity. So here, blue is upwards. So again, here you can see there's convergence here, then there's upward motion, and there's divergence along. Yes?
No, sorry. I'm sorry to make you go back, but
No.
how are the two coupled again?
They're coupled through continuity of pressure across the interface and continuity of vertical velocity. So here is a trouble, as you can see, the solution very nicely transitions. That's just what the coupling conditions make you do. There's also wave radiation, for details, there's also wave radiation condition all the way to the top of the stratosphere. That's just so that energy profit is up. So this is what, like you can clearly see a very different structure in the troposphere and stratosphere. In the troposphere, you can see evidence of both the barotropic and baroquinic modes, right? It's not easy to see the barotropic mode, but just the fact that there's non-zero vertical motion at the tropopause means that there's a barotropic mode. And the baroquinic mode, you can see it's associated with here, this convergence, there's vertical velocity and divergence aloft. That's the baroquinic mode. We see that there's an eastward tilt with height, in the stratosphere. There's also one, it's hard to see, but there's also one in the upper troposphere. And that's just consistent with upward propagation energy. So you have a wave, the wave propagates energy somewhere. You can't have propagation into the surface of the Earth. It has to propagate energy up. And that's consistent with an eastward tilted height. Now, in reality, you actually observe a westward tilted height in the lower troposphere, and we didn't account for that here. And that means that other vertical modes might be important, although some people I've talked to today have heard my opinions about it. But that's just to say that we're not accounting for all the bells and whistles, and we're just trying to account for the interaction with the stratosphere. Okay, so you know what the structure of a leaky equatorial wave looks like. I'll show you here now. Next, what I'm showing you is the growth rate. So the growth rate is basically a measure of how unstable a mode is. So the higher the number, the more unstable it is. And in the case where you have a rigid lid at the top, the growth rate is more or less constant with the wave number. This is a measure of the horizontal scale. But under the leaky lid, here the growth rates are actually maximal at the largest scales, and the growth rates decay with the scale. So you can think of this as the stratosphere is acting as a scale selection mechanism, because you have the largest growth rates at the largest scales, and the growth rates just decay with the smaller scale you get. And that's actually what we observe in the real world. So people are looking for scale selection mechanisms. Why is all the power concentrated at the largest scales? The phase speed doesn't change all that much. It's not important. So basically what you're seeing here is that the stratosphere acts as a reddening, a noise reddening of the power spectrum. It's trying to concentrate the energy at the largest scales, and the smallest scales, the energy doesn't. Things don't like to grow. And you might ask yourself, well, why is the case? So in the black line here, I plotted the vertical group velocity. And this is, you don't have to do this coupled troposphere-stratosphere model to learn about the vertical group velocity, but the vertical group velocity is just a metric for how fast a wave is propagating energy up into the stratosphere. And basically the reason why these waves are not growing is because they're propagating all the energy up into the stratosphere, and that means they're not allowed to grow in the troposphere. So the stratosphere acts as a noise reddening of the tropical power spectrum. Now you can do this for all different kinds of waves. So the different colors are just different kinds of equatorial waves in the troposphere. And so the solid line is the rigid lid case, and the more dashed things get, the leakier the stratosphere is. And what I'm going to show you here are the power spectrum composites from observations. And so you can see for the Kelvin wave, the power kinds of maximizes around zonal wave number 3 or 4. That's what you see for the blue line here. The Kelvin wave is the n equals -1. If you go to something like the antisymmetric spectrum, the inertial gravity waves, the n equals 0, that's this red line here. You see they maximize somewhere around k equals 0 or 1. And that's not exactly what you see here, but there's some reason to believe that these are qualitatively providing the similar results. Yes?
You might have mentioned this earlier, but what parameter are you specifying for like the leakiness of the?
It's the stratosphere stratification, the S term. Sorry, that's a good question. Yeah, I'm just changing the value of S, so I'm changing the buoyancy frequency in the stratosphere. And so all this is showing is that the stratosphere has a filter on it. Like if you put in a rigid lid, it has a filter on it, and it likes waves that propagate very quickly to the stratosphere. It's acting as a high pass filter. So really only small scale waves can efficiently move into the stratosphere. And this is kind of like a scale selection mechanism that the stratosphere acts as on the troposphere. So this is one hypothesis for why we see why that power spectrum looks like the way it does. Cool, and I'll stop here. This is the first part of the talk. It's not considered the meat of what I want to do, but we actually introduced the model that I'm using and use it to understand very simply how it might affect waves in the tropics. So, if there's any questions right now, feel free to ask.
I guess I have a question, which is, how do you imagine the atmosphere might promote development of leaky spots in the stratosphere, or the tropopause in the tropics? Are there events that can do that, or is it some sort of a internal variability, perhaps?
Well, here, if you just take the stratification to be constant everywhere,
right,
then it already acts as a mechanism. So you have like small scale gravity waves that propagate really fast into the stratosphere where they deposit their momentum, whereas the larger scale stuff likes to stay in the troposphere and propagate for a long time.
Yeah, and I guess I'm wondering if you think it's possible that the tropopause boundary can be softened in certain places. And if so, it allows larger waves to dissipate, or I mean to disappear into the stratosphere. And if you do think so, how might that happen, even though it's not in your model?
Yeah, so one of the things is that when the tropopause is cold, the stability is reduced. And the tropopause is coldest over the warm pole region. So it might be that the waves are it's leakiest over there, where you have a lot of gravity waves
Okay.
that emanate over the tropopause.
And so it can be regional for various reasons such as that.
Such as the stability being
Okay.
different. Yeah. Or in this case, the model, I haven't shown you how I non-dimensionalize the stratification, but what's important in there is like the buoyancy frequency, for instance. So the buoyancy frequency can change with the temperature, mean state temperature changes.
Okay, thanks.
Any other questions? Okay, great. So the next part of this talk, I'll be talking a little bit about stratospheric modulation of the Madden-Julian Oscillation. Now this is kind of a very big topic recently because, well, I'll explain a little bit why later, but this work will be published soon. It got accepted a few weeks ago. Okay, so the Madden-Julian Oscillation is an eastward propagating planetary scale mode in the tropics, and it has a period of around 30 to 90 days. So this is just a schematic much better than I can draw. I stole it from somebody. I forgot to give the credits. Oops. But basically you have, this is when the Madden-Julian Oscillation convection is centered over India, but you have upward motion centered over the region of convection. There's precipitation, divergence aloft, and typically away from that you'll have subsidence, and it's usually sunny and dry. And this whole thing moves eastward very, very slowly, and it takes around 30 to 90 days to circumnavigate the globe. This is kind of what it looks like. This is the signature of what it looks like in the upper troposphere. So just flip it, and that's what it looks like in the lower troposphere. But here you can see that the colors are precipitation, or you can think about the OLR signal, and then here there's divergence, but in the troposphere just think of the opposite of the arrow signs. So I like to call this like a gill-like shape, or a swallowtail. Okay, so there's another mode of oscillation in the tropics, but this is in the stratosphere. It's called the Quasi Biennial Oscillation. It's less famous, I think. But it's a stratospheric mode of variability where the winds in the stratosphere change from west to east and back. And it takes around 2 years, which is why it's called quasi-biennial. So this is equatorially, the zonal wind on the equator in the stratosphere, where the positive or red ones are westerly winds and blue ones are easterly winds, and you can see it's a very, very nice, periodic switching between the winds in the troposphere, the winds between easterlies and westerlies. And it's a very well-studied phenomenon. We know how it works. We know how to generate it in a model. We know how it has not eluded us. We know how this works. Now the really, really fascinating thing is that the QBO has been, in observations, it actually modulates the strength of the Madden-Julian Oscillation. This is a figure I stole from a review paper, but basically through thermal wind balance, when the QBO is in its easterly phase, so when there's winds coming from the east in the stratosphere, you have cold anomaly, but the tropopause is cold. And when the tropopause is cold, you actually observe a much stronger MJO. So a lot of these other claims, like slower eastward propagation, increased cirrus cloud, there's less evidence for that in the observations. But without a doubt, you have increased strength of the Madden-Julian Oscillation. And it's the opposite when the QBO is in its westerly phase. The tropopause is warmer, and you have a decreased strength of the MJO. And this has been a big problem in our community because nobody has been able to simulate this in a model. Every single attempt at being able to replicate this relationship in a climate model has not been able to. And there hasn't been a lot of positive results from efforts to study this. And it's a big problem because the Madden-Julian Oscillation controls a lot of the subseasonal predictability and variability in the tropics, but also across the globe. And if we can't get this right, then we just have no hope it just means we don't understand what's going on with the Madden-Julian Oscillation. Yes?
I'm sorry to interrupt again. Is there a distance difference from strong to weak between the ascent and the descent? in the circulation?
How do you?
You know, the rainy column has strong updraft and the dry column has downdrafts. Is the distance between those two laterally different if you have a strong MJO versus a weak one?
I'm not sure. Typically, how people measure MJO strength is they don't really take that into account. They just look at low frequency variability. So it's sometimes people do take into account the zonal wave number, but I'm not sure of that. I'm not sure about that.
Thanks.
Okay, so, and this is, this is a big problem. But first of all, the Madden-Julian Oscillation is really hard to simulate in a climate model to begin with. So I personally think this has been fascinating, and the reasons why we don't know it are, I hope that we'll be able to figure it out soon. So the goal is to actually, can we investigate this stratospheric modulation of the MJO? But instead of taking the route we're trying to simulate all the processes explicitly, we're going to use a simple theoretical model. You might think, wow, you're overreaching with your simple theory, but maybe we can get some insights. And so the first thing I want to start with, again, is observations. And what I want to prove to you here is that clouds are really important to the MJO. So what I'm showing you here, this is from a field campaign, Togacor? Do you know this?
Yes, that's how you say it.
Yes, okay. Togacor. And so basically, what you're seeing here in the dashed lines is the outgoing long-wave radiation over the Togacor region, the field campaign, and the black lines are it's the entropy deficit, but you can think of it as log of the equivalent potential temperature near the surface minus log of the equivalent potential temperature in the upper troposphere. But you can think of it as a moisture deficit, so a deficit of moisture. And so basically what you see is there's a huge, huge correlation between that quantity, the moisture deficit, and the outgoing long-wave radiation. And this has been well studied in our field, and this has led to parameterizations. For instance, in our model, we have the radiative cooling parameterized as, here Q dot is the radiative cooling. Some strength is a scaling of the radiative feedback times the mid-level moisture entropy. In the linearized framework, it's just a deficit. Yes?
Real quick, why the equivalent TEB is the equivalent potential temperature?
Yeah, they use T,
Why?
but it's actually theta.
Okay.
Yeah.
Why is it formulated that way?
Log?
No, just wondering, it's the 975 equivalent potential temperature minus the 300
hectopascal equivalent potential temperature.
Yeah.
But it's the log of that, so it's an entropy.
Okay.
Yeah. Did that answer your question?
Not totally.
Did I just talk it?
Don't worry about it.
Okay, we can talk about it offline.
Yeah, I'll ask you later.
But basically here you can see that the idea is that the more moist the troposphere is, the more clouds you'll have, and that reduces the amount of radiation that you can emit to space. And the further evidence is that when you include this parameterization here, this Q equals CSM, into this linear model that we have, you actually get something that looks like an MJO-like mode. Here I'm showing you the solution for when the stratosphere wind is 0. So, we haven't put any wind in the stratosphere yet. This is just the control simulation, or the control mode. But here you have this, the Rossby gyres, the Kelvin wave-like solution. This is like the swallowtail figure we saw before. And you have, convection or upward motion centered on the equator. Because it's a first baroquinic mode, it's the opposite in the tropopause, and as you move up, you can see some other fancy patterns in the stratosphere. So I think the community has gradually been gravitating towards the fact that clouds are really important for the Madden-Julian Oscillation. So it makes sense that if there's anything that the stratosphere could affect the Madden-Julian Oscillation, it's the clouds. Yes?
I'm sorry, how is the E parameterized in this then?
The radiative cooling is parameterized as, it changes as a function of the mid-level moisture, the moisture deficit. So if the moisture is if there's more moisture, the cooling is reduced.
And then putting moisture into your model.
That's a separate parameterization that we did. It includes linearizing the column integrated entropy equation.
Okay.
That's how it's a separate variable that's predicted. I glossed over that because I didn't want to talk about it, but
That's fine.
if you have more questions.
You're asking about the leak.
No, I'm just asking how the phasing all works out.
Okay, so it's clear that radiation is, modulation of radiation is important, in my opinion. So let's go back to observations again. And here what I'm showing you is composites using a variety of sources. So this is the red line is the outgoing long-wave radiation composite. Sorry, this is a composite of the MJO from NOAA's interpolated OLR data set. The contours are the water vapor anomalies, so positive meaning there's more water vapor, that's from reanalysis data. And the shading is the ice cloud fraction, which is from a polar orbiting satellite radar. And so basically what you see, co-located with positive vapor anomalies, so convection is occurring here, you have the greatest reduction in outgoing long-wave radiation, and also the largest amount of ice clouds. But you also see, what you don't see in the vapor fields is you see a really strong eastward tilt with height in the ice cloud fields, and that might be important, or you'll see that it's important later. So what's actually modulating the radiation? Is it the water vapor? Is it the ice clouds? What you can do is just take this cross-section. So you have the ice clouds, cloud fraction. There's also another component. You need the ice water content. That's also estimated by a satellite. And you put in the water vapor, you just plug it into a radiative transfer model, and you say, what is the radiative forcing of the ice clouds? So you can say, if you just put in the ice clouds and you leave out the water vapor, and as opposed to leaving out everything, it gives you what the radiative forcing of the ice clouds are. And what I'm showing you is the radiative forcing of ice clouds in the dashed line as compared to water vapor. Oh, whoops. And this at the dashed line, that's that vertical cross section, and then the dot dashed line is just eastward of that. And you can see here, it's a function of, so this has to do with ice microphysics, but it's a function of the effective radius of ice. Basically, we don't really know to a good degree what that is, so that's why I was exploring the sensitivity of that. But you can see here that basically the ice clouds have a much, much stronger radiative forcing than the water vapor anomalies do. So the ice clouds are what are dominating the mid-level moisture, not the greenhouse feedback. So if we go all the way back to this, that parameterization is wrong, because it's not the moisture, it's actually the ice clouds. But the two are correlated, right? The two are, I mean, where you have most ice clouds, you have a lot of water vapor anomalies. Okay, so what is contributing to the ice clouds? Well, here we again use observational data. But here what I'm showing you instead is, now the contours, it's a little confusing, sorry, but now the contours are ice cloud fraction, so these are positive ice cloud fraction anomalies. The shading is the vertical velocity now, so the vertical velocity I just took from reanalysis data. And you can see, I don't show you what's below this, but basically they're very well co-located below about 10 kilometers. But as you move up, you can see here that the vertical velocity anomalies are well correlated with the ice cloud fraction anomalies. And if you don't believe me, I just took this is just a schematic, but here I'm plotting the ice cloud fraction and the vertical velocity at 14 kilometers. And there, I mean, obviously the vertical velocity data is much noisier, but here you can see there's a very strong correlation between vertical velocity and ice cloud fraction. So if you're well versed in the ice cloud literature, these could be anvil clouds, but what I'm interpreting this is large scale forced ice clouds. So there's waves that happen in the upper troposphere, and they're forcing the production of ice clouds. Okay, so far, I think we've shown that ice clouds are really important for MJO destabilization. And so the hypothesis we have is that the stratosphere is actually modulating, because the vertical velocity is important for ice clouds, it's somehow modulating the structure of vertical velocity in the troposphere. And there's actually evidence of this in the observational literature that, for instance, upward propagating Kelvin waves or upward propagating waves in the troposphere into the stratosphere actually modulate ice cloud fraction. And so you can think of some amount of wave energy propagating upwards and modulating the ice cloud fraction. in the upper troposphere. And okay, so hopefully I've convinced you that ice clouds are really important. It's not just the moisture or the water vapor in the lower troposphere, it's also about the ice. So what we need to do next is include some kind of proxy. We need to replace that parameterization, right? Because it's the ice clouds that are important, not the water vapor anomalies. So you can take the water vapor prognostic equation. This is not the equation, the full equation, but that I used in my actual paper, although if you're interested in it, I'm happy to talk more, but I just kind of made it simpler for this talk. But basically you have a prognostic equation for water vapor, and it's the only source term is vertical convection of vertical transport of water vapor. And here, this upsilon term is just the non-dimensional coefficient for the strength of vertical convection. You then linearize the ice cloud fraction equation, so you assume that ice cloud fraction is linearly proportional to the water vapor anomaly. Now, you might ask how in Earth I got this equation. But, so what I did was I took Chem 5 macrophysics and linearized it. That's probably not the right way to go about it, but it's an equation, right? And this scaling term, it's all in the appendix of the paper. And then you assume that the perturbation radiative heating is some proportion, there's some contribution from water vapor and some contribution from ice. So some other details that might be important here, but it's not important for this talk, is that this parameterization occurs at a single level. So here we just assume that it's the water vapor or the ice at 15 kilometers that's important. In the non-dimensional model that we have, we assume the tropopause is at 16 kilometers. So the stratosphere starts at 16 kilometers. So you can imagine 1 kilometer below the stratosphere, and that's kind of around where the climatological cloud fraction of ice is at its peak. You know, we're constraining all these non-dimensional coefficients here. It's just all magic, but we're constraining them using observations and radiative transfer calculations. And the last thing we're going to do is modify the stratosphere equations. Before, we just assumed there was no wind, mean wind, but now we're going to include a mean wind. This is also a lot of work. I don't want to bore you with all the details, but just know that we massaged the equation, so we have now a mean zonal wind in the stratosphere. So the first thing we're going to do is look at the solutions of the model when you do not have ice cloud feedbacks, but we're going to vary the stratospheric wind. So just keep in the back of your mind that we haven't touched the ice yet. We haven't replaced that parameterization. We're just looking at how the solution changes when you just change the stratospheric wind. So I'm showing you horizontal cross sections. So this is X dimension, Y dimension. These are the same composites I showed you before, where the contours are geopotential, the arrows are wind, and the shading is the vertical velocity. So this is not the pressure vertical velocity anymore, this is the actual vertical velocity. So red is upwards motion. And this is what the solution looks like in the troposphere, at the tropopause on the top right. And this is 2 kilometers into the stratosphere and 5 kilometers into the stratosphere here. And this is when there's easterly winds in the stratosphere, so constant easterly winds. And what you can see here is very, very nice structure, but in the stratosphere you can start to see separation between the equatorial component, this is the Kelvin wave, and the Rossby component, which are these huge gyres that are polards. And then the phasing basically decouples as you move up. And the reason for that is that the vertical tilt of these modes is different, but that's not important to know. Now I also show you the solution when there's a westerly wind, and I'll just like toggle between these two so you can see the differences. And immediately what you'll see is that first, the troposphere signature is not too different, the structure is not too different, but the stratosphere signals are really, really, really different. And all I'm changing is the stratospheric wind. And so notice what you'll see is, right, during the westerly stratospheric wind, there's almost no upward wave propagation near the equator. And that's actually a well-known result that Kelvin waves cannot propagate up during westerly winds, and the opposite is true for Rossby waves. And it's more clear if I show you the vertical structure here. So this is the vertical structure on the equator. When you have easterly winds, the Kelvin wave likes to propagate up, and when you have westerly winds, it's strongly damped. So you have damped upward propagation of Kelvin wave under westerly winds. This is the solution that looks like, so this is on the equator where the Kelvin wave is most active. Off the equator where you have, this is off the equator where you have the Rossby gyres. Here you can see the structure is very, very different under easterly winds or westerly winds. Under easterly winds, the solution actually was extremely barotropic. There's almost no baroclinic mode for the Rossby gyres. You know, the structure is slightly different. What I wanted to point out here is that the vertical velocity here, which is the red, peaks around, you know, somewhere around 13 kilometers, and it is much lower when you have easterly winds in the stratosphere. So it's a little odd, right? Because all we're doing is changing the mean wind above this pink line, but we're changing the structure in the troposphere a lot. But nothing in the troposphere is changing. Only the mean wind in the stratosphere. And I think that's there are similar results from Lorentz back in the 1960s in the extratropics, but it's kind of fascinating to see this also in the tropical atmosphere. So basically, what I'm qualitatively showing here is that the vertical velocity profiles are more top-heavy, or they're concentrated more in the upper troposphere when you have easterly winds as opposed to westerly winds. And I know that was a lot all at once, so maybe if anybody has any questions, I'm happy to answer them.
How can you see the vertical velocity profile differences between these two?
I have a more quantitative slide later, but basically like this deep red, it's hard to see.
Okay.
Plus,
So it's the red shading is that?
Yeah, where you see it start to decay, so here it's around 10
Yeah,
kilometers.
okay.
But I have a more quantitative figure for it.
Okay.
and these are zonal winds, but when you're off the equator, you can worry about meridional winds too, contributing to the divergence, right? And we don't see
yes.
those, but they must be manifest in the differences at the
Yeah,
near and
because
the
these are
troposphere.
zonal vertical composites. I
Yeah.
wanted the zonal wind. But there's also meridional wind, but
Are they they must be very different from easterly to westerly winds, are they? I mean, I don't know how else you can sustain a different vertical motion profile off the equator.
well, things can be like zonally, like if the zonal circulation satisfies most of the continuity, then
Even off the equator it does?
I don't know. I haven't looked at that
Oh,
yet,
okay,
but
okay. I don't want to slow you down.
Well, the tropospheric structure is very similar between the two. That's
Yeah, it's a stretch to say it's similar at 16. That's what I thought. When
Yes,
you first
at
said it,
16
and now I
kilometers
think I have a
it's-
reason why I think it's a stretch. I think there has to be a difference there.
yes, there is.
Okay.
Yeah. Okay. So now what we're going to do, so before I said, okay, I'll take out all I haven't put it together yet, but now I'm going to actually impose, instead of a constant wind, I'm going to actually impose a realistic QBO-like wind. I'm going to now also include the effects of ice. And in the paper, we've separated these out individually, but for the sake of the talk, I'm just going to put these all together. We're going to allow for dynamical forcing of ice clouds. So now we have, instead of instead of the water vapor being responsible for the radiative perturbations, we're going to let the ice be responsible for the radiation perturbations. And then the last thing we're going to do, we're going to account for QBO-induced mean stratification changes. It's a mouthful, but it's basically, remember how under easterly QBO, it's cold at the tropopause, and the westerly QBO, it's warm at the tropopause, so that induces a slight change in the stratification. So we're also accounting for that. And this diagram is very confusing, so I want to explain it first. What I'm doing is showing, so on the x-axis is the phase of the QBO, so this is the easterly QBO, westerly QBO. On the y-axis is the stratification in the stratosphere. So larger means it's more stratified, meaning that it's warm, for instance. Warmer at the tropopause, colder at the tropopause. And I drew this line here because I'm showing you that in a QBO west, the Earth is kind of around this regime, where you have westerly winds and things are more stratified. Under QBO east, you have weak easterly winds and a weaker stratification. So that's why I plotted this line here. And what I'm showing you is the growth rate anomaly from just the center, which is no wind and just the mean state of 40, which is around average. So basically where you see positive, and what I'm plotting is the growth rate. So this is a measure of the instability of the mode. So you have, the mode is more unstable when in a QBO easterly phase, and less unstable in the QBO westward phase. And this is consistent with the relationship that we observe, although, you know, I like to say there's a 50% chance of getting the right answer, so this is not definitive by any means. And so what's going on here? And what's going on here is that the stratospheric wind and the stratification is actually modulating the top heaviness of vertical velocity. So this is the more quantitative plot. So on blue is the height of the peak of where vertical velocity peaks. And so that's just plotted by the blue line. And then the red line is showing you the difference between the QBO east vertical velocity peak and the QBO west vertical velocity peak. That's just from our solution. It's small but non-negligible in the tropics, and it becomes much larger as you move away from the tropics. So basically what's happening is, you know, the vertical velocity is being modulated by the stratosphere, and that vertical velocity leads to a stronger forcing of ice clouds. And ice clouds are the things that you care about when you're thinking about destabilization of the MJO. So yeah, are there any questions about this before I move on to the next section, which is maybe more convincing?
So you got this from, you said linearizing the CAM microplan.
Yeah, so in CAM microphysics, the macrophysics equations are basically, they say, as the relative humidity increases, it scales kind of like quadratically with, the ice cloud fraction scales quadratically with the relative humidity. So you linearize that, you just take some place along that quadratic slope. And it's not great. The CAM microphysics scheme is also, you know, the macrophysics scheme is also kind of ad hoc, but I didn't know how else to. You could also just not say it, just say it scales linearly and just assume it's some coefficient.
So it's at every level then that you're doing, every level has that relationship?
No, I'm just taking this parameterization at a single level because,
Okay.
yeah, I mean, I show in the paper sensitivity results to the level you take at, but it's not super. As long as you take it to be in the upper troposphere where there are ice clouds.
Okay.
Sorry, I saw a hand.
Yeah, I was just going to ask, what's the Mariana length scale you're looking at here? Like, what is -4 equal, like mid-latitudes, or just like?
Oh, I'm so sorry. You mean the lengths? Yes, so I non-dimensionalize everything. This is about 10 degrees latitude. So one unit is around 10 degrees latitude.
Okay.
So this is 20 to 20, and that's 50 to 50. Obviously, this model will not, you don't expect this model to work in the extratropics. So I would be focusing more here. Anyway. Sorry, thanks for bringing that up. I totally did not explain it. Okay, so now I have some sexy modeling results, but it's not really results because I haven't gotten too far with it yet. But this is the System for Atmospheric Modeling, SAM. It's a cloud permitting model. You can run it in global aquaplanet configuration, where you just fix the SSTs. It's 20-kilometer resolution, so convection enclosed permitting, and there's no convective parameterization for those of you that care. It's very interesting, and what I'm showing you is just the OLR. It's just a movie of the OLR. You can see there's some funky things going on in the extratropics because it's fixed SSTs everywhere, but in the tropics, which is very small here, it's narrow, -10 to 10. You can see some stuff propagating east, some stuff propagating west. There's a lot of variability. There's lots of stuff going on. But there's actually an MJO-like disturbance in this model. And I'm showing you, here's the Hofmuller diagram of the wave number 1 component and the power spectrum on the right. And so this is the power spectrum that you saw earlier, but here you can see this big peak here in the wave number 1 slow propagating mode, although I admit that it's not too different from the Kelvin wave dispersion relation. You need to do more analysis, and I'm not showing that here, so you just have to take my word for it. It has some non-zero meridional wind. Maybe it's something like a Kelvin wave, mixed Kelvin wave MJO, but something that looks like an MJO. I cannot, you know, that's part of modeling, is that you don't know what you're modeling is ever actually the real thing. Okay, so it has something that looks like an MJO. This is not what the MJO looks like. And if you can change some aspects of it to get something that looks like more realistic. But here you have an eastward propagating mode that is slow. So what we're going to do is have the sedimentation velocity of ice and double the sedimentation velocity of ice. So ice sedimentation velocity is just how fast ice falls out of the troposphere. It's an extremely sensitive variable, and from talking to modelers, they tell me that it's one of the last things they tune in a climate model to get the mean state radiation correct. And so we just explored this space and see what the sensitivity is. So basically you can think of when you have the sedimentation and velocity of ice, you're allowing clouds to stay in the atmosphere longer, and when you double it, you're making the ice clouds fall really fast. So they have less of a residence time in the atmosphere. And this is what the MJO signal looks like when you have this sedimentation velocity of ice or double it. So what this is showing is that the amplitude of this big MJO-like disturbance in this idealized model is very sensitive to the ice microphysics, meaning that the amplitude can double or halve if you just change the ice sedimentation velocity. And this is not the only knob you can tune of ice microphysics in this model. And ice happens the climatological peak of ice happens in the upper troposphere. So if somehow the stratosphere can change the ice in the upper troposphere, that might be a way to modulate the amplitude of the Madden-Julian Oscillation. Okay, so I don't think I've answered what really I haven't run a bang up climate model or simulation to show you the Keeble-MJO relationship, but hopefully I've given some kind of hint to whether or not cirrus clouds are the key to this problem. I put out some evidence that ice clouds are key to destabilizing the Madden-Julian Oscillation, and here the mechanism is that the easterly QBO decreases the stratosphere stratification, which increases the magnitude of the barotropic mode, and the barotropic mode increases the top heaviness of vertical velocity, which in turn leads to a stronger forcing of the ice clouds. We have some preliminary modeling results that show MJO sensitivity to ice clouds. Of course, more work is needed. Some of that is ongoing, but we will see whether or not it leads to anything useful. And after today's talk, I hope I convince you that the stratosphere is important in modulating things in the troposphere. Tropical intra-seasonal variability can be especially sensitive to the stratosphere. It's kind of a form of downward control in the tropics if you're an extratropical person. In the stratosphere, we think about downward control a lot. Downward control meaning stratosphere downward influences the troposphere. And I think this is really important to understand because the footprint of climate change is the opposite signal in the troposphere and stratosphere. It's warming in the troposphere, but cooling in the stratosphere. And so being able to understand how the stratosphere influences the troposphere is important, especially if we want to make predictions about how things will change with warming. So, of course, thanks for having the patience to sit through this talk, and if you have any questions, feel free to email me. I'm happy to chat more offline.
All right, we have time for a question or two.
Could you comment on what the westward tilt of the tropopause might, what you think it might do in terms of differences between the eastern and western Pacific?
The westward tilt of the tropopause?
Yeah, so like the fact that it's deeper over the warm pool and shallower over like...
Yeah, so it's not too much deeper. I mean, you could measure that in like tens of meters, I think. It's not too large. And people have also commented on the fact that the tropopause slopes in the meridional direction as well. That's definitely something that we did not account for. I'm not sure if it'll make a difference. Again, one of the biggest approximations we make is that there's an infinitesimal jump between tropospheric dynamics and stratospheric dynamics. That's not the case at all in the real world. I thought about putting another layer so you could get something like a transition layer, but then I didn't know how exactly to represent the dynamics of that. But basically, you could, if you did that, if you added a third layer and just made the mean state a little bit different, you could maybe exaggerate some of these changes. But I wouldn't focus too much on the exact details of the things we did, but more so in that the stratosphere plays a big role in modulating the vertical velocity structure, and that has a big role in modulating ice clouds. So I know not a super gratifying answer, but.
Any other question? Dan?
I'm supposed to let the students ask first, so that's, I don't want to
Anybody?
take anyone's comment.
Questions?
Sorry to create an awkward situation there. So yeah, I'll just ask the question. I guess in terms of the mechanism for the reason why the ice clouds are creating that instability, is this just that the heating projects more onto both of the vertical modes in the troposphere, or is it that it's phasing differently, or it's just amplifying, or what?
So actually, the barotropic mode does not have a thermodynamic signature. It's not excited by heating.
Okay.
It's excited through coupling with the baroclinic mode. So you can imagine the heating is driving the baroclinic mode. The baroclinic mode projects onto the barotropic mode through stratospheric interactions. You can also couple it through surface friction or vertical wind shear. I did not put that into this component. But the ice clouds are only acting on the baroclinic mode.
Okay. And so that destabilization is what, just enhancing the heating?
The destabilization, yeah, it's the ice clouds are further destabilizing the MJO through heating.
Okay, there's no like phase. I mean, like you could introduce those the ice clouds in a way that changes phasing of the heating with respect to.
Oh yes,
the
that's
structure.
exactly what I glossed over this, and it's in the paper, but here, right? There's a tilt here, so the heating can be offset from here, and this tilt might be important in the phasing between the heating from the ice clouds and the actual center of convection. I explored this a little bit in this model, but yes, it's definitely something that is possible, and a lot of people have commented on this eastward tilt with height, and I think this is important as well.
Do you get that out of the editor simple?
Yeah, so I have an eastward tilt with height in my model. You can change an eastward tilt with height through the stratosphere. I glossed over this because I didn't want to, but yes, this eastward tilt with height is replicated in our model. You can change the eastward phasing based on the stratosphere. And then,
Other student questions? Yeah.
Thanks. You might have answered this. I was wondering, like, sort of how exactly does the barotropic component change the top heaviness? Like I'm thinking like barotropic is constant with height, so even if you increase or decrease
the
it.
barotropic vertical velocity is linear with height. It's the zonal winds. Oh wow, it's a very big photo. Here, the barotropic. But remember, omega is the integral, so the integral of a constant is a linear function.
Okay. So one more question, and the interest of time, so it's already past 4:30, but yeah.
I'm curious.
Go ahead.
I was just curious if you could just clarify for the Cirrus ice cloud production, based on that vertical velocity and the top heaviness, is that making an assumption that you have a lot of kind of entrainment from the high convective clouds, and that's what the Cirrus is forming from, or is this already, Cirrus that is present?
Yeah. So there's two in my perusal of the literature. There's two kinds of cirrus clouds or ice clouds that matter. They're the anvil clouds, which are kind of leftover remnants of convection that spread out near the tropopause, and sometimes there's overshooting convection. People talk about how that leads to cirrus clouds in the transition layer. There's another kind of clouds that other observations have been advocating for, which are clouds that are forced from large-scale vertical velocity, so large-scale positive vertical velocity. In this case, we have zero details about entrainment and detrainment. We're just saying that the large-scale vertical velocity forces clouds. And I cited some observational work on that, but you can actually see a modulation of ice cloud fraction by what we think are upward propagating waves. So those are the kinds of clouds that we're thinking about. We're not, there's no like entrainment, detrainment time scale in this model.
All right, everybody, in the interest of time, thanks Jonathan for your talk. Feel free to stick around and ask some questions.